Well, here we are. I feel like I should say something, but I don't know what there is to say. I'm gonna miss you guys, but I still have another month with you, so I'm recording this well in advance. So, but I am gonna miss you guys, and I hope that we'll all be together soon. And I hope you will come visit me in my office. I post my office hours on my door when I have office hours in person, of course. So that information will be on my door. And my door is in Don Myers. My office is the one that has origami in front of it. Well, who knows? Maybe it's fallen apart by now, but I'll try to put it back up. Maybe you can find me. When you're walking through the building, just say hi. Say, hey, I was in one of your online classes over the past year. Because just say that. And I'll be like, oh my gosh, you're real. Okay, so, all right, back to the lesson, the last lesson. So I want to talk about some things you need for the last worksheet. And the first are a couple of really common models. And this is going to take a lot more time to explain than for you to do it. So let's dig in. All right, so in physics, we have usually position of a particle is represented by S at time t. And whatever this position is, we take the derivative of it and we get the velocity at time t. So whatever it is, I'm just saying S prime becomes V. And then we have one more leg of this journey and we get, I mean, this can go on forever, honestly, but these are the three things that we normally do. We usually do the derivative of velocity is acceleration, and then we get acceleration as a function of time. And so what we obviously want to do is give you the easiest possible example. So often we have like, let's say a line. It could be a constant horizontal line, but I'm just going to make it a little more interesting for you. And then what will happen is you'll end up with, let's say, you know, like some kind of parabola as, you know, if you go backwards, and then you'll end up with some kind of like, I don't know, cubic. I'm just doing this suggestively. This is not really, the functions I've drawn are not in that special relationship with each other. I haven't been very careful. The point is, if you start with a cubic for position, you'll end up with a parabola for velocity, and then you'll get a line for acceleration. If you start off with a parabola for position, you'll end up with a line for velocity and then a horizontal line for acceleration. So those are two really common types of problems people will give to students. So just be aware that that's how these three go together. Position, so this is the position, velocity, and acceleration. So that's the relationship that you need to know for one of the questions. Oh, and of course, if your acceleration is negative, it's called deceleration. It's just negative acceleration. So let me just type that out. Okay, so anytime you see decelerating car, the car decelerates, you can just replace that, swap that out for negative acceleration. Same thing. Okay, next concept I want you to know about is this notation for exponential growth. Okay, so the pieces of this guy are, this would be your initial starting value, your y naught, or you call this initial values. And this would be, for example, the money problem or a bacteria problem would be an exponential growth problem. This is the growth rate. And as long as r is greater than 0, it's a growth. This is the start time. So t minus t naught is the passage of time. Now, if you want to make this into exponential decay, it looks exactly the same, except that then the rate is going to be negative, and then you're not going to be usually talking about money or bacteria, then you're usually talking about half-life questions. Okay, so it's really the same. It's just that you're actually just moving in the opposite direction. And in both of those cases, your model is going to look like y prime is equal to ry. So if r is positive, then you have a growth, and if R is negative, you have a decay. Okay, so that's what you've got. And like for money in bacteria, you're going to end up with, as t goes infinite, you have a growth, and over here, as t goes to infinity, you go to 0. You're decaying. Okay, and so these problems, we rarely see them except they're with respect to 0. So you're talking about quadrant 1 problems, and they're going to either shrink down to 0, or they're going to kind of look like they came from 0 to begin with, and now they have an exponential growth. So they're just really with respect to sort of some kind of absolute 0. So what if it's temperature, a temperature question? We very rarely deal with 0 Kelvin on this planet, so we have to modify this model. Okay, so with a temperature question, everything is with respect to the room temperature. That's the colloquial word for ambient temperature. And you're going to either have things growing up to ambient temperature or sinking down to ambient temperature. So I want you to just think in terms of hot coffee will start off hot and go down to room temperature, whereas like a bowl of ice cream is a good thing to use to model the other effect. And in either case, you're going to be approaching room temperature in the long term. So what's important is you're going to say that change in y is going to be proportional to the difference between its current value and its limiting room temperature ambient value. Okay, so whatever that is, and the reason I put a negative is the negative is a restoring factor. Like, so when we did this going down to 0, the negative brought us down to 0, but this is just kind of we're just shifting it so that that's our new 0. Restoring to the y limit here. So that means the absolute value, like this actual r, is going to be positive, and we put the negative in the formula to emphasize the fact that we're going to converge on that room temperature. So it's a very common thing we do in math and science. If we know that the coefficient's always going to be negative, we hate negative signs sufficiently that we put the negative sign right in the formula so that the coefficient itself can be positive. Okay, so this is always going towards the limit as t goes to infinity, so that's why the coefficient would be negative, and we put it right in the formula like that. So this is an example of a very special kind of differential equation. There's a whole class of them that have this following property. So I'm going to just let you look at that for a second. But anything that has the format y prime equals f of y only, i.e. f of x and y does not depend on x, so you can just write it as f of y. This thing has a special name. It's called an autonomous differential equation. And you have to be careful in mathematics about the word autonomous, because this is an overloaded term. Okay, this is overloaded. That means if you just like look up the word autonomous, you will have no idea what you're talking about. But you have to look up autonomous differential equation, then only then you will understand what autonomous means. So you have to give the context of differential equations, or you're going to get a bogus answer that has nothing to do with what you're looking at. Okay? This means it's essentially horizontal shift invariant. Okay, so that's what we're talking about, horizontal shift invariance. This means that if I come out, I have a hot cup of coffee, and I sit down at a table and I'm drinking my coffee, whatever, then 10 minutes later somebody does exactly the same thing, they're not going to experience it differently. They're just going to be shifted in time, right? So this means some kind of stable environment, all right? Or maybe laws of physics are at play. Okay, something is stable in the environment that is causing the differential equation to only depend on your start time. Like, so you're only, if you start later, everything's going to happen exactly the same way. You're just going to start later, literally. But you'll experience the same thing as if you would have started earlier. So, so that's just something to be aware of. Those are really special and fun and easier at least to visualize. And so we're going to zoom in on one and see what it looks like. Okay, so I just made this example up, and I'm going to give you some axes, but notice that y prime equals 0 if y equals 0 or y equals 3. So I'm going to just put little dots here to tell you that this should be a stable, not necessarily stable, this is an equilibrium. And this one up here is an equilibrium. We'll find out if they're stable in a second. And so one thing, in this case, you can actually just look at x3 minus x, just to get a sense for what's going on with this parabola here. It's going to have a minus x squared term in it, so we know it's a downward facing parabola. So if this is, just to give you an idea, this is positive, negative, negative over here. So we're going to have, for when y is greater than 3, the slope is going to be negative. Y prime will be negative, positive in the middle, negative down here. So you can just sort of figure this out. You can say, okay, your curves are going to kind of look like this. They're going to look kind of like exponential curves here. They're going to peel away and go like that. Okay, and there's no point in drawing more of them, but I could if I wanted. But the whole point of having this be autonomous here is I can do the following. I can just say, fine, I have a whole million copies of this. I can just like say this happens over and over and over again. The whole point of it being autonomous is everything just gets shifted over as many times as you need. Okay? And so some of these are stable and some are unstable. So this one is stable because you see it's sucking in the solutions. This one's unstable because it's kind of like, think about walking on a tight rope. If you're a tightrope walker, if you're walking on the rope and you make a small mistake, you're going to fall off and you're not going to come back on. Here, I want you to think the other one is kind of like you're walking in some kind of a ditch. You know, like you're inside the ditch, and then if you try to go outside the ditch, it kind of tries to suck you back in again. All right, so that's kind of just a mental idea that helps you understand what you're looking at. So for example, I have this over here on the web page. You can just fill in your differential equation and graph the direction field, and then you can see right here, oh cool, I didn't even know you could do this. This is so cool. Right, and just play with this. Oh, this is so much fun. Okay, anyway, have fun with that. That will possibly help you on your homework. I mean your worksheet. I want you to also realize that you don't have to use y and t. You can use y and x. You can use w and t, w and x. It doesn't really matter what variable name you use. Okay, I just made this up. Kind of a recurring theme here. The variable name is irrelevant, but k is your independent variable, and you know it's k is a function of t or x or whatever. And so here I don't have a k in here. They're all like either plus or minus something. So at k equals 4, we have some kind of equilibrium, right? And at k equals to 10, we have some sort of equilibrium. And we also have one at k equals -7, but the one at -7 maybe looks a little different than we're used to. So let's just think about this for a second. So we have one at 10, 7, no, so 10, 4, and -7, but -7 has a double root, and this guy is flipped around backwards. I really hate it, but like that's what we do. We just write one of them backwards to introduce a negative, so we know that we're going to go off negative in the end. We're going to loop around here, and so I'm just drawing this function x minus 4, x plus 7 squared times 10 minus x, just so I can get a sense for what it looks like. All right, so most of this is negative, but between 4 and 10, it's going to be positive. So this is going to be negative. All this is going to be negative. It's not going to even see that horizontal axis there. It doesn't care. It's going to still go down. So you're going to get solution curves that look like this. Bing, bing, bing. This is going to go wing. Like this is a bad picture, but it will probably cross through this, what's called like a semi-stable, it's a semi-stable solution. It's going to suck. If it wiggles just a tiny bit, it's going to suck itself away from this semi-stable solution, but it depends. If you have a pure math problem, then your solution will end up probably on that equilibrium, which is semi-stable. This guy is a stable equilibrium and an unstable equilibrium. Okay, so I messed with this a lot. Here's the thing we were just looking at. I don't know why it doesn't take squares, so I just took the same factor and put it in twice. But I found that if I made the t values very, very small, I got prettier arrows. Okay, because these are rather steep, and that's why if you make the t only go from like plus and minus 0.01, you get prettier arrows here. But you can look at some of the solution curves. I don't know why I'm only getting little pieces here. Yeah, I'm not sure what's going on. I don't really know how to use this tool, but when I'm clicking here, I'm only getting teensy little pieces, but that's okay. It's a fun toy, and it helps you reassure you that what you're doing makes sense. So for example, what I plotted for you on the other page, I said between 4 and 10, I see myself going up like this, and this is happening here. So I should be able to hopefully follow, like you could follow with your mouse, play connect the dots, and just until it does one of these kind of things. Okay, so you can just see that line where it goes. And you can see they are attractive up here. That means they attract down to that solution. And then at 7, where is 7? So this is an interesting one because it shows you that it's there. Oh, I clicked on 7. That's amazing. And so that these curve away, right? So it does what we've predicted it would do. Okay? So that's just a lot of fun. And just keep in mind, it doesn't matter what you call your dependent or independent variable, it behaves the same way. So that's all for that. Okay, so for number 4, I thought you might want some hints. And the reason why is just the way it's written. It seems confusing, but you have to realize that it's just structurally identical to something like this. So I'm going to make up something that's structurally the same and talk about it instead. And literally we just change the variable names around, so don't worry about that. And then you have something like your y equals 50 in this case. What does that mean? Well, remember I said this means you're going to restore. In other words, we're going to restore to the limiting case, which is this is the limiting case here. So that means we're going to be going towards that ambient temperature or whatnot. Okay, and there's really no meaning down here to the y equals 0. Like a temperature of 0 is not really that special. I mean, it is in Celsius because water freezes, but it doesn't really matter in terms of like you can go above and below it. There's no, we're not talking about absolute 0 Kelvin here, so it has nothing to do with it. So if you want to analyze what's going on, one thing that is useful is like, think about y versus y prime. This is like something you can do. Like I did in the other pictures, you can say, wait a second, I actually just can plot minus 4t minus 50, just as a way of trying to figure out what's going on. But I could also just make a list and say, well, when y is 50, y prime is 0. When y is 100, I don't even care what it is, just if it's positive or negative. If y is 0, oh, you know what? It is positive. What about if it's negative 50? It's positive. So I'm just trying to get my bearings here and try to make sure I'm pointing those arrows in the right direction as we go off to infinity. And keep in mind, if I had written for y minus 50 and made this the differential equation, then we would have flipped those. This would be going up and those would be going down. They would completely be unstable. So that little negative sign matters a lot. And then you're going to be asked to solve once you have your equation sitting in front of you. And feel free to change the variable names if it helps you, right? So if you want to solve this, how do you go about solving it? And this is separable, so you just write dy dt is minus 4y minus 50, and then you put like the y minus 50 down here, minus 4 dt, and go ahead about your merry way. You're going to get a plus constant, a constant of integration on one of the two sides. It doesn't matter which. In the worksheet problem, your initial condition is provided in question 4. It's part of the word problem. It's stated in words. So you take those words and you use that to figure out what C is. Sorry, I didn't know where my mouse was. Okay, so you have to figure out what C is, and then you go from your general equation. So you're going to have your general solution, you're going to find C, and that's going to give you your particular solution. And then, only then, can you answer the question as stated on the worksheet, because you have to answer it based on the particular solution. The general solution will not help you. You have to get all the way to the particular solution to answer the question. Okay, so this hint is for question 5. It's the last question in the whole worksheet set, like the whole course, all the worksheets in the whole course. It's asking you to assume that Galileo was wrong about being wrong, or was right when he was wrong. Anyway, we're going to assume the speed is proportional to the distance that an object has fallen. So remember, v of t is the derivative of the location, which is the distance from the start. And we're going to assume it's proportional to d of t. So actually this symbol, to mean proportionality, you go like that. Or you can say, let's say we kind of play fast and loose with this proportionality symbol, because now I'm using it as a variable, but if I go like this, I'm using it as a relational operator. So I'm just going to use it this way. I like using it that way. Okay, so that means d prime is some constant times d, and so we can just rewrite that as d capital, change in d over change in t, which is proportional to d, and then that's separable. All right, separable, or guess and check, because you should recognize this guy. It's just going to look like what? Think about it for a second. Okay, so it's just going to be ce to the constant t, like that proportionality constant. So what is this cryptic thing that Robinson is saying? Well, I just think I will give this to you outright. So the initial condition at t equals 0, the object hasn't fallen yet. And so that is the kind of weird situation that our friend found himself in. So Galileo was actually claiming something that, honestly, it's really hard to visualize this. You're saying that before it starts falling, it hasn't fallen yet. And at the moment when it begins to fall, it hasn't gone anywhere. So if this formula is true, it can't ever go anywhere. And clearly, we all know that it goes somewhere, like the objects fall. So what Robinson's trying to get at in this exercise, I think, or whoever wrote this, is that there is a fallacy here, and the fallacy is that this equation cannot be what the relationship is. This is not how a falling object can function, because we could never start the fall. Okay, so I'm not entirely sure if I agree with that or not, but because you would think that just with air pressure it might start moving off in some direction. I don't know, but whatever. It's an interesting thought experiment, and you can go ahead and follow the logic on that. And that's the last question in the last worksheet. And I hope you've enjoyed doing these worksheets. And obviously don't hesitate to ask me for help on this worksheet or on anything in the course. I want you to do really well. I want you to get good grades on all the quizzes and all the web work and all the written assignments. And well, I guess if you're watching this video, you're in the home stretch. So congratulations for getting this far, and I will see you in class. Okay, bye.